Hello everyone, my name is Zheng. I am from Shen University, and I'm glad to be here to share the work accepted by the IEEE ICC 2021, which was finished by me and two co-authors, Shen and Chen. The title of our paper is Design and Analysis of Uplink and Downlink Communication for Federated Learning, and I will introduce our work in the following 5 aspects. First of all, I would like to talk about the background and motivation. As we all know, AI is one of the most important technologies today, in which data collecting is the basic prerequisite. However, the collecting will become more and more difficult for several reasons, like business competition, prices, or rules on privacy protection. In the recent years, an emerging technology like federated learning has been proposed to solve the above problem, in which the user only needs to upload the local modules instead of raw data through multiple routes of exchange and aggregation of modules organized by the centralized server. A high-performer global module is finally Chen. But in FL, communication overhead is one of the primary challenges because of the huge scale of today's DNN modules and the interactive characteristic of module chaining. Hence, in this work, we focus on reducing the communication cost of FL. As for the system module, or to say the framework, we combine FL and wireless communication as shown in this diagram. Here to show the global object function, 4 steps are implemented interactively. Firstly, clients download the module using downlink channel, and then I update the module with their local datasets separately. Later, the client will upload the updated modules using the uplink channel, and finally the server aggregates this module and create a new global module for next round chaining. Actually, the communication aspect, including quantization, encoding, modulation, and more problems, like multi-access. In this paper, we pay attention to the design of quantization. Next, I would like to detail the uplink communication design first. There are two significant problems which answer. The first one is what to transmit. There are two choices, namely the weight or the weight differential. From a pure learning perspective, there is no difference to choose each one of them. But even to be safer or to be more exact, we should choose the former one. However, when considering the quantization problem in uplink communication, the latter is a much better method, since the dynamic range of weight differential is much smaller comparing to the weight itself, which can make the quantization more precise with limited bitwise. We will see the benefit more intuitive when later solving the experiential result. And the second problem is how to transmit. We design a quantizer with 4 steps, including scaling up, rounding, limiting, and scaling down. The first and the last step are to make the quantizer be able to match the very range of the weight. As for the rounding step, we use stochastic rounding, which rounds the vary to its two closest points with different probabilities relative with the distances. The stochastic rounding is an unbiased method, which is very important to reduce the quantization errors. And Besides, we also make analysis on the convergence of these different congestion schemes for the uplink communication, and with the following two assumptions, which are both quite general and widely used in federated learning. We derive the convergence result of both direct transmission and DT. The most important finding is that to convergence with the same rate of O1 over T, increasing the bitwise is necessary for direct transmission, while a constant bitwise is enough for DT. So we can see that DT is actually in a better scheme, both in the application or in the theoretical perspective. And next, I'll give some experiment results, and these two figures are to see the impact of the quantization gain and the routing function. Here, TQ means tilde quantization gain is selected, and you can see that this improves the performance significantly. And also, we can see that the SR is better than NR in both the final module accuracy and also the convergence speed, even with fewer bits used. In addition, we observe an interesting phenomenon that the impact of K, which means the client amount for each route, is different for NR and SR. For NR, more clients participate, may even reduce the performance, while for SR, this observation does not exist. And also, as the convergence result tells us, an increasing bitwise is necessary when not using DT. So we verify that the increasing weight can make a performer better comparing with the result using fit bitwise. Also, we show the enormous benefit of DT, which 1 bit quantization is enough in this case. And now let's move to the design in downlink communication. The problem is that DT, which we have shown to be a very important optimization method, is no longer applicable for FL with partial client participation. Since for a newly participating client, it does not have the last global module as the base, and you will fail to reconcile the global module for this round if we use DT in downlink communication. So we have to design other schemes to enhance the performance of the downlink. And from these two figures, we can see that the barrier range varies from layer to layer in DNN modules, which is actually a common phenomenon. This means that the optimal quantization gain for each layer is different. So based on this observation, we can design another enhancement method called layered quantization. To use layered quantization, we first divide the gain into two parts, namely base quantization gain, which is only relative with the bitwise, and also another one is layer-specific quantization gain, which is relative with the dynamic range of each network layer. So when implementing LQ, the base gain is firstly determined with the given bitwise, and then the server calculates the empirical CDF of each layer and takes the 90 potential barrier alpha to determine the layer gain. Finally, these two gains are combined together to be used in a quantizer similar with the one used in Uplink. We also derive the convergence result of FL with quantized downlink communication, and the result shows that increasing the quantization level is still necessary since DT is unable to use in this case. Next, I would like to design experimental result of the downlink communication with quantization. The first one shows if we use a poorly designed quantization scheme, the errors will impact more on the downlink. Here, the FL still fails to convert even with 6-bit quantization for downlink model. Fortunately, a carefully designed scheme still works well. With the basic quantization scheme, which is similar to the uplink communication, just without DT, the loss can be controlled within 4% with 4-bit quantization, and with layer quantization as an enhancement, the loss can be further reduced to less than 2%. And here is the result of quantizing both the uplink and downlink on different communication on different data sets under both IID and non-IID case. We can see that the proposed communication schemes are quite effective as they have to save at least 80% communication with negligible performance loss. For example, for many data sets with IID setting, 4 bits for both downlink and uplink is enough. And even for more complex cases, like CIFAR10 datasets with non-IID setup, 6 bits for downlink and 4 bits for uplink have very good performance. Finally, let me give the summary of our work. We described a comprehensive network combining FL and wireless communication. Several efficient schemes are proposed for uplink and downlink quantization, and also make theoretical analysis to get the convergence conditions. The experimental results are quite exciting. Since on the data sets we considered, we can save more than 80% bandwidth with mirror loss. And in some special case, 1-bit or 2-bit quantization is actually enough. Overall, our work can be helpful to address the communication bottleneck of federated learning. This is all of my presentation. Thanks for listening.